All right. You guys ever heard of Marie Curie? Not Mercury. Marie. That's why I said it slow like that, Nicholas. Marie Curie. She's from Poland. And when she was, and I'm just going to tell you a quick summary of her life. Is that okay? Story time. So Marie Curie, she was born in Poland. She grew up in Poland, and well, she was interested in sciences. Okay, they didn't have what? She things weren't the way they are here in America. Everybody didn't just go to school and. So anyway, she was interested in the sciences, and she actually wanted to be a scientist. And so this was in the late 1800s, and back then, girls weren't scientists. That just wasn't what happened. But she wanted to be a scientist. This is really what her interest was. And so she graduated high school, I guess. I don't know exactly how their school went. But she wanted to go to the university and get her degree in science. She actually liked physics. And she went to the university in Poland, and they says, hey, no women allowed. You can't come here. What are you thinking, right? So this is back in the time when the ladies just stayed at home. When what? Fossils. Yeah, not that long ago. Actually, some of them probably were. But anyway, so her and her sister, their mom died, and so they kind of...
Allie Sessions, please come to the front office. Allie Sessions to the front office.
They kind of were taking care of the home, I mean, they had their dad, but he was always at work and stuff. And anyway, they was talking. They says, we want to go to college. So let's go to France and go to college there. And so they decided they was going to let her older sister go. She wanted to be in the medical field. And so they let her go first while she took care of the things at home. But she didn't just wait for her. Marie, she was trying to learn as much as she could on her own. And she didn't have internet, right? It wasn't that back then. And so it was a lot harder to learn things back then than it is today. No YouTube, right? So it was tough for her, but she wanted to learn this stuff and wanted to understand and wanted to become a scientist so bad that she was going to put forth the effort to do it. Yeah? And anyway, so her sister got back. She got her medical degree, and then Marie went to France, and she got her degree in physics. And then she got her, I don't know if she got her master's in physics, can't remember. But then she got her PhD in chemistry. And well, this lady's not just a smart lady, but she's a determined lady. And she was the first woman to receive a Nobel Prize in science. And she was the only woman, I don't know if she's still the only woman, she was the only woman to receive 2 Nobel Prizes in 2 different sciences. So she got a master's in physics, PhD in chemistry, something like that. And anyway, so in the process, so one of her Nobel Prizes, she discovered polonium. That's element number 84. And I don't know if you recognize the importance of polonium. Look at the periodic table, see if you can. I know those chairs are in the way. Do you see anything different about polonium than any of the previous elements? What? It has a bracket. What does the bracket mean? Okay, and that's what I said. But more than not naturally found. I mean, the reason why is because it is unstable. It doesn't, well, it can, but it's unstable. It decays. So you mentioned decay, right? So it decays and becomes something else. So anyway, that's the one that she discovered. And anyway, she when she was in France, she was working with this guy, Paris. He's a French guy, right? And his name was Perry Curie. And so she ended up marrying this guy, right? And anyway, he decided to stop what he was doing and help Marie because it was more interesting. And anyway, he ended up dying, and so she took his place in the upper seat of the college or whatever. And she was a professor and everything. And anyway, she made a good thing for herself, and she ended up dying with cancer. Now, why is that? Yeah, she was around under these unstable isotopes, and it was decaying, and it emitted radiation, right? Is radiation a good thing or a bad thing? Both. But there's two different types of radiation. We got the radiation that we're familiar with. Where do we get radiation from? The sun, the lights, right? Okay, yeah. So yeah, electromagnetic radiation. So this is like what? Radio waves? You guys know radio waves, right? What's the next highest energy? Microwaves. And then infrared. X-rays a little bit later. Infrared, so you can't see those. And then what do you get? Light. The visible light. And then what's above visible light? We got ultraviolet, and that's what gives us sunburns, right? And then after that, we got X-rays. We all have an X-ray? And then after that, we got gamma radiation. And gamma radiation, it's just high energy light. That's all it is, okay? But it's a little bit too much. I mean, our atmosphere blocks most of the UV rays, and that if it didn't block all the UV rays, yeah, it would be toast, right? You ever think about going to the moon or something? Not think about going there, but if someone goes to the moon and they're in the sun the whole time, it gets really hot there. Why? There's no atmosphere to protect them, yeah? And anyway, so if we didn't have the atmosphere, well, those UV rays would cook us. But it also X-rays and gamma rays would come in, but they're blocked. And besides, you don't get a lot of gamma rays coming from there, but anyway, you get some. Are we good? All right, so anyway, that's Marie Curie. So, ladies and gents, she did something that she really loved doing. She enjoyed it. And she went to work. You guys have a job? Raise your hand if you have a job. And keep your hand raised if you love your job and you want to work there for the rest of your life. Okay. Yeah. Well, yeah, okay. Yeah. And that's how it was when I was growing up. I got a lot of good experiences, but I'm certainly glad I'm not a coal miner, right? But I love all of the experiences I got at each job that I was at, and I'm glad I'm not that, right? It'd kind of be boring. In fact, my wife, her dad started a company building cabinets, and she built cabinets from the time she can start at 18 years old all the way until just this last year. And so what's that? 25 years almost. She worked there for 25 years, and she didn't like it. She didn't like working there. And we all got to work. You guys know that, right? Anybody feel like, whatever, I'm not going to work. I'm just going to be a stay-at-home scumbag. right? I'm just kidding. I didn't say stay-at-home mom. Those are good, but it seems like nowadays you got a lot of people that I just don't want to go to work. I remember when we was growing up, everybody had a job, and we just always worked from the time we was little, and we just always worked. And now it's like, everybody doesn't have a job. It's like, that's weird to me. But anyway, a lot of you guys have jobs, so that's good. So we need to. What I'm trying to get at is we need to find what our niche is in life, so that we enjoy what we're doing. Because we're going to go to work anyway. We just as well enjoy it, right? Anyway, so you might have to do some uncomfortable things to get there, like go to school, right, and learn. That's hard. It really is hard to learn, guys. That's one of the hardest things there is that you're going to do on earth is to learn. You guys realize that? Yeah, it's hard. But you got to be disciplined and determined to learn it. But if you don't master the content, guys, it's not going to be as fun. It won't be. Anybody have an idea what they want to do? What do you want to do? Be a surgeon? Yeah, if you was bad at it, would you like your job? Oh, I killed that guy today, right? Yeah, you have to be good at it. Otherwise, it's like, okay, I hate my job. I don't want to kill another person, right? But you have to be good at what you do. And so when you go to school, I mean, yeah, you're going to get a lot of experience actually doing it, right? That's why in the medical field, you have to go to school for a lot of years, because part of it is you got to go actually work in the hospitals and under somebody, right? Same thing with the teacher. We have a year of student teaching where you go under somebody and they kind of give you the ropes and help you to know how to be a teacher rather than just come here, okay, class, I don't know what to do, right? So you kind of have to have both. The education to kind of learn the material and then the experience. But anyway, that's just a side note of Marie Curie's life. So anybody can do anything they put their mind to. Do you guys believe that? Do you believe you can do anything that you put your mind to? Good. All right. So let's start with when Marie Curie was doing her work, she come up with this term. Radioactivity. And what is radioactivity? Somebody kind of mentioned it. The difference between nuclear and chemical. Nuclear is spontaneous and chemical is not, right? So radioactivity is the spontaneous emission. And what does spontaneous mean? By itself. It doesn't have anything else to get it to do it. Like a chemical reaction, you have to actually mix the baking soda and vinegar, right? You mix them and then they react. And then they react spontaneously after that. But if you just have a bag of baking powder or baking soda and a gallon of vinegar, nothing's going to happen, right? They don't spontaneously react until you mix them. So spontaneous emission, what does emission mean? Stuff comes off, right? Emission of particles and or rays from a certain isotope. $235. We'll talk about that a little bit later. That's That's going to be in section 25.3. But because that's not decay, we're actually making it happen. So it's not spontaneous. That doesn't happen spontaneously. But great question. But we'll get there. All right. We okay with radioactivity? Okay. Next word. So we're going to go over a few definitions. I know this is boring, but guys, if you don't understand the vocabulary, then when we talk about it, it's like, oh, what is he even talking about, right? So nuclear radiation. So we just talked about electromagnetic radiation with light, right? With radio waves all the way to gamma rays. That's electromagnetic radiation, and it's just transfer of energy. But nuclear radiation is radiation coming from the nucleus of an atom. So don't write it that way. I mean, you can, but nuclear radiation, they are particles or rays being emitted from a radioactive source. So radioactivity says spontaneous emission of nuclear radiation, basically, right? Because here we have particles or rays, and this is particles or rays. These are the same thing. Any questions so far? Okay, another one. Radioisotopes. I want you guys to think about a definition of radioisotope. From these other two definitions, don't tell me right now, but come up with the definition of radioisotope. Just think about it for a minute. I don't want you to give me an example. I want you to give me a good definition of a radioisotope. Got this, Kenneth? Anybody have an idea?
An isotope that emits particles or rays spontaneously to
Okay. Good. What's a quicker way to say that, Josh? An isotope that is radioactive. A radioactive isotope, right? So I'm going to add one word to it, an unstable or radioactive isotope. We know what an isotope is. We know what radioactive is. So we don't have to put a bunch of words into that, do we? I mean, you can. Unstable or radioactive isotope. So, Nick, what's an example of a radioisotope? It's barely said 1 minute ago. Uranium-235, right? Yeah, it's unstable, and it spontaneously emits particles or rays. Yeah. That has what? Yeah, but not only those elements. We'll talk about those in just a minute. We good? What's your question? Not all elements. No. But some isotopes of every element will be unstable. Yeah, you can't destroy it. Is there air resistance for those electrons?
No, because they're smaller.
They're smaller than that, right? Okay, they're part of air. But so there's no resistance to slow them down, and yeah, so do we know everything about it? No, there may be, right? But as far as we can tell today, is not all isotopes are unstable. Not all isotopes will do this. Okay? All right, so let's talk about the difference between chemical reaction versus nuclear reaction. We did a little bit, but let's go a little bit deeper. And you'll need to know this in fact, you need to know all this for the test. So the test will have definitions, right? These will be on there. So make sure we know them. So let's do chemical reactions versus nuclear reactions. Chemical, we says, changes what? Electrons change, right? And nuclear, what changes? We're going to call them nucleons. Gotta spell it right. Nucleons change. What are nucleons? Let's write that definition. Yeah. Nucleons are the particles of the nucleus. Yep. Protons and neutrons, that's it. Now protons and neutrons are made of other particles, but that's nuclear particle physics. We won't go there. But the main particles of a nucleus the big particles of the nucleus are protons and neutrons. Yeah, protons and neutrons are made of something else, but we're not going to go there. Good? All right, what else? For a chemical reaction, we can... Sorry, what was you going to say? Yeah, so we could say that, yeah. Is spontaneously... let's use a different color here. Spontaneously reacts. And we can say non-spontaneously, right? And for chemical reactions, then we can change the rate of reaction. And how do we do that? By doing what? Apply more energy to it, right? Give it heat, give it light, give it sound, give it whatever. So change the temperature. Temperature's the main one, but that's not the only one. Temperature, but yeah, like Josh says, change the energy. What'd you say, Josh? No, everything's not. Well, kind of. Yeah. But it's not usable energy yet. It's potential energy, right? But anyway, so we got temperature change will change the rate of reaction. If we make it hotter, it's going to react faster. We kind of know this, right? We did this with the flip the lid lab. We did this even, in that chemical reaction lab where it got hotter, and so then it reacted, right? What else can change the rate of reaction? Any ideas? Pressure changes. Well, if we increase the pressure, that means it's getting hotter, right? And for nuclear reactions, we cannot change the rate of reaction. You can't make it go faster. You can't make it go slower. It's going to do what it's going to do regardless. Kind of cool, right? And this is why Marie Curie got cancer. Because she was playing with this stuff that's just always decaying, always emitting this radiation. She can't slow down. She can't speed it up. It's just happening.
Is there a way to make it stable?
Yes. But if it's stable, it's no longer radioactive. Obviously, right? It's something else. We'll talk about it. Are we good with the differences between chemical and nuclear radiations? Or chemical and nuclear reactions? Oh, there's one more thing that will change the rate of reaction. Sorry, I forgot. Is adding a catalyst. So we'll talk more about this in a couple units. But catalyst is something that speeds up the reaction. But it doesn't really partake or take part in what the product is. Yeah, an enzyme, yes, is an example of a catalyst in like our bodies, right? But also, you guys ever heard of a catalytic converter on a car? You guys know what the purpose of that is? Yeah, it's to make bad gases not as bad, right? It completes the combustion. But what you're doing is you go through that catalytic converter, and what it does, it speeds up the reaction of combustion, and then you have your not as harmful gases come out. Good? We'll talk more about catalysts later. So you can't even use a catalyst for a nuclear reaction to speed it up. It's just, nothing will happen. Good? All right, next let's talk about the 3 types of nuclear radiation. What are they again? Oh, maybe before we get there, what makes something radioactive? If it's unstable, what makes it unstable? How many electrons it has? What do you think? How many neutrons it has? Remember, the nuclear doesn't matter about the electrons. That's chemical. The nuclear is determined by the nucleons. It's not just the number of neutrons, but it's neutrons and protons. So, neutrons and protons determine if an isotope is radioactive. So now let's think about this. You with me, Kenneth? What's the charge of a proton? Or positive one, right? So they're both positive. What happens? Where are these protons in the atom? In the nucleus, next to each other. How is that? What do positive charges normally do? Repel. So there's something holding it together. What is it? It is the neutrons. We call this the nuclear force. You guys ever heard of the nuclear strong force? This is the strongest force we know, and that's on the test. Nuclear force. Just the strongest force that we know of. And it kind of pulls these things together. And like Nicholas said, it's the neutrons act as nuclear glue. And let's take a look at this. If you look at these elements on the periodic table, the one with brackets, why did these, and it's, none of the upper ones have brackets, but everything from past 83, and this is on the test, everything past 83, not everything, but most of them have brackets. Yeah? Why is that?
They're unstable.
Sure. But why is that? Use something we already learned. For example, let's look at calcium here. That's not unstable. I mean, you might be able to have an unstable isotope of calcium, but in general, most of them, they're not unstable. Hope not, because they're in our teeth, right? They're in our bones. But how many protons does calcium have, guys?
40 or 20.
What? 20. How many neutrons does most calcium have? How many? 20. Has a mass of 40, right? That means 20 are protons, 20 are neutrons, right? So we have 20 protons and 20 neutrons. Now let's look at polonium. How many protons does polonium have? Somebody tell me how many neutrons polonium has.
Is it 104.5?
Yeah, well, I don't know. Has 209 as the mass number, right? How do you know that's not the atomic mass? How do you know that's the mass number?
It's a 20.
Because it's a whole number. And it's in brackets. Okay? So 209 minus 84 is 125. Has a lot more neutrons than it has protons. Why is that?
How is bismuth or not? Because it has
We're not talking about bismuth for a minute. We're talking about polonium.
It's less protons.
I know, be with me. We'll get there in a minute. Answer my question first, and then I'll answer your question. Because there's a lot of protons that are trying to push apart. You have to have more glue. Eventually, this is not taking anymore. So everything above 83 will be radioactive. Even though some of those aren't in brackets, they're still radioactive. Okay? Some of them aren't as radioactive, so they're not as unstable, but they still are. Good? That are? There are some that are not. Can we make them? Yeah, we'll get there. Okay? Are we good? All right, now let's get into the three types of nuclear radiation. So I'm going to make a table, and I want you guys to know everything on this table. I would write this down, study it. Oh, we forgot. Oh, my gosh. It's Kimber's birthday today. We got to sing happy birthday, don't we? Me. You guys ready? Happy birthday to you. Happy birthday, every now, to you. Happy birthday, dear Kimber. Happy birthday to you. Happy birthday. What? What? Oh, it's because really, you guys weren't singing, really? Oh, you guys don't like Kimber? Nothing. You guys think I'm nuts, don't you? Good. All right. Well, happy birthday, Kimber. Hope you have a good day. So here we go. So types of nuclear radiation. So I'm going to put a table here. So we got the type right there. And we got what it's consisted of, what it consists of, what its symbol is, what its charge is, what its mass is, and common source. All right. So let's do the first type is, and I'm going to just give you this table, and then we'll talk a little bit more about each one of them separately. Sound good? So write this down. So the first type is alpha radiation, or alpha particle. So we talked about nuclear radiation are the particles or rays, right? So alpha is an alpha particle. Is that how you spell particle? Yeah. L-E? Yeah, it didn't look right. Okay. So alpha particle consists of a helium nucleus. Is it a helium atom? No, it's just the nucleus of a helium atom. And so, can you guys figure out what the isotope symbol is for an alpha particle? What's the element? Helium. What's the mass number? Any guesses? 4. And what's the atomic number? That is the symbol for an alpha particle. Did we talk about alpha particles already? Remember in Ernest Rutherford's gold foil experiment? He shot alpha particles at the gold foil. There, what's the charge? If there's no electrons, it's just the nucleus. Positive what? 2. Has 2 protons and no electrons, right? And what's the mass? Uh-oh, I wrote that in the wrong spot. Plus 2 over in the charge, and 4 is the mass. Are we good? And a common source is polonium-210. So that means polonium-210 will undergo alpha decay, meaning spit off an alpha particle. You with me, Kenneth? How are you? All right. And the next type of nuclear radiation, any questions there? We'll talk more about it, but the next one is a beta particle, also a particle. And a beta particle is an electron. That's all it is. And where does it come from? The nucleus. Isn't that wild? Crazy, right? We'll talk about it. Remember how I said neutrons and protons are made of different particles? Yeah. And electrons are one of them. Crazy, right? What's your question? Okay. So what's the symbol for an electron, guys? E. Well, we want the isotope symbol. What's the mass number?
0.
And what's the charge? Do you see how this is the charge, guys? There it is. So the charge is -1 and the mass is 0. And one that undergoes beta decay is carbon-14. And the last one is gamma rays. Why are these rays and not particles? Because it's just light. It's electromagnetic radiation. This is light. Okay? So it's just high energy light. And the symbol we use for gamma is just a Greek letter gamma. That's what a Greek letter gamma looks like. Kind of. It's kind of like a curly Y, R, whatever we want to call it. Looks something like that. So, yeah. No, a fish looks like this. That's alpha. But anyway, okay? And what's the charge of light? Any? No charge. It's 0. What's the mass of light? 0, right? And so if you want, you could put a 0 here and a 0 there, right? But if you don't want to, we just know they're zeros. Good? And the source of this is a good source that decays gamma is cobalt-60. All right, we good with the 3 types? All right, let's go a little bit deeper now. Or do you need this still? Anybody need this chart still? Okay. So let's talk about alpha. Alpha radiation or alpha decay. What does decay mean? It's breaking apart, right? It's disintegrating. So here's an example of alpha decay. We have uranium-238. And this undergoes radioactive decay. So this is kind of the same way we write chemical reactions. You guys, did we ever write a chemical reaction for you guys? So if we have sodium and we mix it with water, it reacts, right? It reacts, and the products that we get is sodium hydroxide and hydrogen gas, and this hydrogen gas is what makes it blow up. Okay? So this is a chemical reaction. And here we're writing a nuclear reaction. So you don't have to really draw this chemical reaction here, but you can if you want. So this is chemical. It's just how we write it on paper. Okay? And then if this is alpha decay, then what symbol are we going to write on the right side of the arrow? The alpha symbol, right? 42He plus, any ideas what we're gonna have left over after it gets rid of an alpha particle? Are we still gonna have uranium-238? No, what are we gonna have? We're gonna have what? 235? How did you get 235? But I know, but how did you get it, Josh? If we start with a mass of 238, did we learn about conservation of mass in this class? Can we destroy matter? No, we can't. Well, can we get more of it? No. So if we started with a mass of 238 and we get rid of a mass of 4, what are we left with? 234. Is it uranium? Oh, let's find out. Part of the law of conservation of energy is conservation of mass, and another part of conservation of energy is conservation of charge. We have a charge of positive 92. We're just talking about the nucleus, right? Positive 92, and we get rid of what? Positive 2, so what are we left with? 90. What element is this? Uranium is 92. This one is 90. Thorium. Do you get how to figure that out, guys? And here's how you check. 234 plus 4 equals 238. You follow? You can do the same thing here. 90 plus 2 equals 92. So easy to check. Just make sure you do that. It's not hard on this one, but the next one's going to be a little trickier for some people. So just easy to check. Any questions on that? Yeah.
For the HK42, is that how it's going
Yes, that's an alpha particle. So what happens is it decays. So if I were to draw this picture here, so here is the nucleus of uranium-238. So it has protons and neutrons in it, right? Just the nucleus. We're not worried about the electrons, just the nucleus. And what happens is a little alpha particle is emitted. So this alpha particle is made of 2 protons and 2 neutrons, right? There's my alpha particle. And what am I left with? A little bit smaller of an isotope, right? Not a lot, just a little bit. And this is thorium-234. Does that make sense? Yeah, and this is always the alpha particle. So when does alpha decay happen? What did we just lose? How many protons and how many neutrons? 2 of each, because we lost the alpha particle, which is made of 2 protons and 2 neutrons. You get that? So alpha occurs when isotope has too many neutrons and protons. So here's another little side note that you need to know for the test. This will be on the test. Isotopes with atomic number greater than 83 will undergo alpha decay. All of those ones with brackets will undergo alpha decay. All of them. I'm not saying only alpha, but they will undergo alpha. We good? Ken, wake up. Head up, please. Any questions on alpha decay? Okay. We'll do some more practice in just a minute. But let's go to beta decay first. So beta decay, an example of this was carbon 14, right? And we have radioactive decay here. You don't have to write this every time, guys. I'm just writing it for now. Radioactive decay. And if it decays a beta particle, what's a beta particle? What is it? An electron, so 0, -1, E. Can you guys figure out what we have left? Try it. These two are examples of what you're going to see on the test. If you can do this one, you'll be golden. This is the hardest one. Did I say it was hard? No, it's just the hardest one. What?
It just changes the charge.
Yep. Okay, what's the mass of our product, guys? 14. It's still 14 because we just lose an electron, which is 0 mass, right? And what's the charge of our isotope? Anybody get 7? Why is it 7? Because 7 plus -1 equals 6. Oh yeah, where did the electron come from? A neutron. How do we know it's a neutron? The mass didn't change. So it changed one of the neutrons into a proton. That's all it did. So let me write this down. We got a neutron. That's the isotope symbol for a neutron. And if it gets rid of an electron out of the neutron, what are we left with? Still have a mass of 1. What is that? That's a proton. Kind of looks like hydrogen too, right? Yeah, because that's what hydrogen is, just a proton. We good? So what's this? What's the isotope? 14,7 what? Nitrogen. Yep. So this answers your question. Is this stable? It is. How do you know? Because what's the atomic mass for nitrogen? 14. Oh, there it is. The mass number is 14. The majority of the elements are not radioactive, so the average is basically the majority, right? And so if we get a mass number of 14, yeah, that's stable. We'll talk more about that next time, or not next time, the time after that. But anyway, so yeah, we can make them stable. We can't make them stable. They just become stable on their own by decaying these particles or these rays. Are you with me? So when does this happen? So beta decay happens when too many what? Too many neutrons and not enough protons, because it changes the neutron into a proton. So that ratio of neutrons to protons has to be right to be stable. Making sense? We got one more and then we can take a little break. How's that? Any questions on beta decay?
How do we even get
because for it to even exist, has to hold these protons together.
So we just lost a
So
neutron.
all of the upper ones, well, you take uranium-238, for example. It decays into thorium. Is thorium stable? No, it's still down there. It's still past 83. And then it's going to decay. It's going to decay. It's going to keep decaying until it becomes stable. Maybe it's going to decay all the way down to carbon. I don't know. And then go back, right? It's going to go back and forth until it becomes stable. So we'll do an activity that kind of shows that a little bit. Not today, though. Good? Love all your questions, though. Okay, we good at that? Okay, and the last one is gamma. We don't call it really gamma decay. Gamma radiation. And this is, we talked about cobalt 60, right? 60, 28. And it undergoes nuclear, or it says radioactive decay. And if we just emit a gamma ray, what are we left with? The exact same thing. Don't write it. We're left with the exact same thing. That won't happen on its own. Okay? Generally, we also get alpha or beta decay happening. So you might get, so on this one I think is beta decay for this particular one. So 0, -1 E. And now what are we left with? Copper, right? And is that more stable? It's not 100% stable, but it's more stable, right? So this still might decay again. Yeah, gamma comes with it. Not always. So here's what you need to know. Gamma occurs with both alpha and beta. Gamma can occur during alpha decay or beta decay. Doesn't have to, but it can. We good? All right, you guys have a worksheet. In fact, you guys want to take a little stretch break first? If you want to stretch up, you can. If you don't, you want to just keep going because this is so fun and amazing and fantastic, then you got a worksheet to practice all this stuff. And if you want to do some together, we can. Maybe we should do one of the bottom ones together because it looks kind of icky, right? No? You just want to do it by yourself? Should we do number 9 or number 10? Number 11. Number 9 or number 10? Number 9. Oh, I thought I changed this and it didn't change. Dang it. There's a typo on number 11. Okay, the typo, guys, is right here. This should be 232 right there. So they're both thorium-232. Did you write that, Kenneth? On number 11? Okay, so let's do number 9. Is that one you said? Okay, it says, write the nuclear equation for the decay of polonium-210. If it undergoes 2 consecutive alpha decays, followed by a beta decay, followed by another alpha decay. Okay. Let's do one step at a time. One step at a time, guys. Okay, polonium-210, how do I write that? Polonium, you look on the periodic table to find polonium. PO, that's 84, and its mass number is 210, right there. You with me? Can you all do this? Okay. And then we don't have to write radioactive decay because we just know it is. Undergoes 2 consecutive alpha decays. We can do this one at a time, or we can do it all at the same time. What do you think? Okay, let's do one at a time. So 2 consecutive, what does consecutive mean? One right after the other. Do you want to do them both together or just one? What? Okay. So let's do 4,2 HE. We're going to run out of room this way. Plus what? We start with 210. We get rid of 4. We have 206. You following me? We have 84. We get rid of 2. So we have 82. That's lead. Now it undergoes another alpha decay, right? 2 consecutive. So there's one. Here's the second one. Oh, we're gonna run out of room, aren't we? Should we do this all in one big bang? Watch. And if you guys don't believe that it works, you can try it the long way. Let's do this. We have 2 alphas and another alpha. That's 3 alpha particles, right? And this doesn't happen all at the same time, but if we do it this way, we'll still find out what the end result is. So we have 3 alpha particles. Do you get that? Plus, followed by a beta decay, so a beta particle, 0, -1 E. And now what are we left with? Can you do that? We start with 210. We get rid of how much mass are we getting rid of for all the alphas together? 12. So we get rid of 12. That's 198. And then we get rid of 0 for the beta, so that's 198. You follow? Anybody have a question up to this point? And you do the same thing for the 84. We have 84. We get rid of what? 6. So that's 78. Then we get rid of a negative. What's that? 79, right? And always check, guys. 79 plus -1 is 78. Plus 6 is 84. And that makes this gold, right? Oh, we can make some gold. The only problem is what? That gold might be unstable still. Does that make sense? How to do that? We could do one step at a time. One alpha, then another alpha, then a beta, then another alpha. We could. But do you see how it's the same thing mathematically? Okay? So that's the way I would do it, just because it's less. If you write less, you have chances for less error. You can still make a mistake, but chances are less. Can we do the rest of these? And if you guys want to, in number 11, we just need to find out what the final product is. If you want to do this all in one big thing, you can. If you want to do one step at a time, you can also do that. So let's do this. Caden? Kenny? Let's do this, guys. Let's practice this. If you don't get it done today, then that's homework, right? Because I'm not going to teach you anything else today. So the goal isn't just to get it done, but make sure it's done right. So I do have an answer key up here. Does anybody have any other questions? Okay, raise your hand if you need help. You feel like you just stuck? Please raise. Oh, are you gonna come and fix this?
Is it broken?
Well,
No.
when I use big blue button, then I try clicking on the speaker and it doesn't work. But I also just noticed that doesn't work either. Or no, not that one. This one.
This one?
So maybe this is,
So the speaker does come from this one.
yeah, not the speaker, but the microphone.
But the microphone does come from this one, I mean.
Yeah. So something is, and I tried unplugging stuff, plug it back in. That's what Kenneth said before.
Yeah.
And oh, you got it. Which one is it?
This is the first one that's on this side.
Oh, I think I did unplug that one. I unplugged both of them just in case.
Yeah.
I'll be right there, Emily. Sorry.